all the details. Sometimes I feel some minor details are a bit tedious. So yesterday in one of the advanced methods for the snakes, I skipped a lot of details and just showed the pictures. So if you want the details, please go through the notes or the book if you can access it. If I go through all of those details, it may be difficult or not so interesting for some of you. And minute details could be skipped because those are parts of the implementation. But if something is not clear, please stop and ask questions. If I go through something fast or skip some details, ask questions. Stop me and, okay? Let's look at another application in the processing of mammograms. And first we saw detection of the breast boundary. So when you have a mammogram, there could be other parts outside the breast that you want to get rid of, and you don't want those pixel values to affect further analysis. A part of the mammogram, I think you can reduce the gain a little. The sound is too much. A part of a mammogram that's important in the analysis by radiologists, important also in the analysis of mammograms for computer-aided diagnosis, but needs to be analyzed separately, is the pectoral muscle. The pectoral muscle appears in mediolateral oblique views, where the breast is compressed sideways at an angle. The other view is craniocaudal, top-bottom. So in the mediolateral oblique or MLO views, the pectoral muscle comes in, and the pectoral muscle has higher density and hence appears brighter in mammograms. And the edge of the pectoral muscle in many images is an almost straight line, but sometimes is curved. So we will look at two methods. One to fit a straight line using the Huff transform. The other to find a curved line, if it exists. If it is a straight line, that's okay too, no problem. And then we can segment the pectoral muscle and remove it, because that's not exactly part of the breast, but it needs to be analyzed separately. So this is a predominant density region in MLO views and can affect the results of image processing if you combine that region with the rest of the breast image, because of the large density difference. And algorithms to detect tumors, if applied to both simultaneously, may not work well. So analysis of the pectoral muscle could be used to identify the presence of abnormal axillary lymph nodes, which could be related to breast carcinoma in some cases, or could be related to metastasis. So it is important to analyze it, but because of the large density difference, it is better to analyze it separately. So first we said, in most cases it's a straight line. If we can fit a straight line approximation, that is useful in other analysis, for example, detection of the nipple, but it might even be adequate to just remove that portion, even if it is approximated by a straight line. So it starts automatically by identifying an appropriate region of interest containing the pectoral muscle, and an approximate breast contour is obtained, and some delimiting control points are obtained for the detection of the skin air boundary, as we saw earlier. And 6 control points, N1 to N6, are marked automatically. So one of these slides should go. This one, if you can remove this. So that's the original image, and we saw the detection of the breast boundary. We have the breast boundary here, and these points N1 to N6 are marked. Or this is okay. That can stay there. Okay, that's fine.
I want that for video. That's
okay. So let's go back. N1 is the top left corner of the boundary loop. N5 is the lowest pixel on the left-hand edge of the boundary loop. The boundary is already detected using the previous method we saw yesterday. N3 is the midpoint between N1 and N5. N2 is the farthest point on the boundary from N5 by Euclidean distance. N4 is the point that completes a rectangle with N1, N2, N3. And that could be inside the breast. And N6 is the farthest point on the boundary loop from N1. So these are the definitions. And the region of interest is defined by that rectangle. We don't need the entire pectoral muscle to fit a straight line. We take a part and fit a straight line to that edge. So we added some geometrical and anatomical constraints, as you will see. So first we apply the Sobel gradient and then the Huff transform. The Sobel gradient gives us the edge, and the Huff transform helps us in detecting straight lines. There could be multiple straight lines, little pieces that come from other parts. Filtering procedure to the accumulator cells in the Huff transform domain to detect the best possible straight line fit to the pectoral muscle. Enhancement of the peaks in the Huff accumulator. So there could be multiple peaks in the Huff transform, Huff domain. And if you can enhance the peaks, then you can separate the dominant peak from the others and helps in selection of the appropriate straight line. Detect the maximum value, and that should correspond, hopefully, to the pectoral muscle edge. So again, this is what we saw. Now, in this case, this box is enclosing all of the pectoral muscle, but it doesn't have to be so. Sometimes the pectoral muscle could go like that. But if you get this portion, it is adequate to fit a straight line. And in this case, the edge is an almost perfect straight line. I'll show other cases later. So the pectoral muscle is considered to be a straight line limited to angle theta between 120 and 170 degrees. And if the mammogram is of the right breast, it is mirrored before processing, so the pectoral muscle edge is always on the left-hand side. So the pectoral muscle intercepts the line segment N1, N2. It has to cut there because this is the edge of the breast. So there must be an intersection there. The pectoral line is present in partial or total length in the rectangle. In this case, the whole thing is there. In other cases, not all of that. And the pectoral muscle is always denser than the rest of the breast, and it is relatively homogeneous. Whereas inside the breast, there is heterogeneity. Sometimes the entire breast could be fairly homogeneous in density, but this certainly is homogeneous. There could be lymph nodes present there, but that could cause a small deviation. So we then define this coordinate system, take the center of the image, and angle theta is defined this way with reference to the horizontal line through the center of the image, and rho is the distance of the straight line along the normal in that manner. So those are the coordinates for the Huff transform. And A is the area of the pectoral muscle that is obtained in the process. A Gaussian filter with sigma x sigma equal to 4 is used to smooth the ROI, so that we're not interested in the details within the breast, the tissues. And Huff transform is applied to the Sobel gradient. If you take the Sobel gradient directly, there could be noise and variations due to the muscles and tissues in the breast. So you don't need that. The Huff transform is this, which we have already seen. Here, x0, y0, the center that is chosen is subtracted, just for reference. That's the origin in this representation. The Huff accumulator is quantized to 45 bins of 4 degrees each. To create the discrete accumulator, you have to discretize the variables rho and theta. So you choose some quantization. We chose 45 bins of 4 degrees each. And the accumulator cells, they're called accumulator because you keep putting a vote into that. Every time a pixel is analyzed, is it on the edge or not? Is it on a straight line or not? If it is on a straight line, for that bin in the accumulator cell, you put 1. You add 1. But you don't have to always add 1. You can add the strength of that pixel corresponding to a line, like a fuzzy membership. So here we use the magnitude of the gradient instead of unit increment. If it is a strong edge, it contributes more in the Huff domain at that coordinate rho theta and xy coordinates as we have used. So this way, it's a non-uniform or selective incrementing of the Huff transform accumulator. It helps in detecting stronger edges and suppress weak edges. So theta values only in 120 to 170 degrees were considered in the analysis. But we don't need 0 to 180 degrees. You don't have to go the whole range because the pectoral muscle will be like that. It cannot be like this. So it could be maybe like that. It has to be vertical, and it cannot be vertical. So it will be, there is a certain range depending on the geometry you have specified. So the Huff transform doesn't have to be computed for all theta and all rho. Rho also is limited by the size of the mammogram, and so this is not just discretized, but also you put spatial constraints in the definition of the Huff transform accumulator. And then we apply a filtering procedure in the Huff domain. In the Huff domain, we have some patterns, as you saw. Straight lines have these sinusoidal. Every pixel on a straight line gives you some sinusoidal pattern, and if there are a number of pixels having the same parameters of a straight line, then those curves will intersect at one point, give you a large value there. But there are many straight lines possible. So there will be many peaks. So how do you choose the correct peak? For that, there is a filtering procedure. All lines intercepting the top of the image outside N1 to N2, or with slopes outside the range 120 degrees to 170 are removed. We are not interested in those lines. They cannot be the pectoral muscle. The x-axis corresponds to 0, and we have seen that coordinate system. And then the remaining accumulator cell values are weighted. You apply a weight using this alpha equal to mu over sigma square A for that rho theta value. Mu and sigma square are the mean and variance of the gray levels in the area A of the pectoral muscle, defined by the straight line with these parameters. So depending upon which line you choose, you will get a certain mean and sigma square. And you apply that as a weight. And the procedure will enhance the Huff transform peaks that define dense and homogeneous regions. If the line comes too much into the breast, then there will be more variance. This will increase, so the weight will decrease. If the density is not high, if breast tissue is included, this density becomes low. Then that weight will be reduced. So if the correct line is found, mu should be maximum, sigma square should be minimum. So this weighting helps in distinguishing between various lines that could be detected in the Huff transform and choosing the correct one corresponding to the pectoral muscle. I'll show examples soon. Okay, so here we have the Huff transform domain. This is rho, 0 to rho max, 0 to pi. But we're not going 0 to pi, we're only using this much. What did I say? 120 to 170 degrees. We are using only this portion. And within that, we are cutting off many other lines. Each point here represents a line in the image domain. So by rejecting all of these other points, we are rejecting some lines that could be detected if you were to find all the peaks here. And further, by applying the weight, only these are highlighted. And among these, you find the maximum. So in the Huff space, we can put more and more constraints depending on what you want to detect, where is it located in the image, and its properties. Not its properties, but the part it would separate from the rest of the image. So here, we are going, this is 0 to pi, but we are using only 120 to 170 degrees. And this is after removing lines intercepting the top of the image outside the region N1 to N2. Let's go back and see here. There could be some line it goes like that. And if it goes outside this, you say, I don't want that line. If the line includes breast tissue, then mu and sigma square, mu will be low, sigma square will become large. So in that manner, you put many constraints. and the processed half space is that. After weighting, in that you find the maximum. And the result is that line for this mammogram. I'll show more later on. You don't get such straight line edges always in the mammogram, but in this case it works well. So in some cases the boundary is not a straight line, so it's a curved line. There could be multiple line segments of different orientation. So we applied Gabor wavelets for directional analysis. It's a little too much. You don't need Gabor wavelets here, but we have again put constraints to minimize computation. We will look at Gabor filters later in more detail in the chapter on analysis of oriented patterns. But Riccardo Ferrari, who did his PhD with me, he applied Gabor filters with many constraints so that computation could be minimized and pectoral muscle edges that are not straight lines could be detected efficiently. So a bank of Gabor filters is used to detect piecewise linear structures, that is, making up the pectoral muscle edge. Here the region of interest is defined to contain the entire pectoral muscle region, because you cannot extend as a straight line like we did in the first case. Let me go here first. So here is the pectoral muscle, which is a curved line. Now one could say, well, let's fit a curve, but in many cases there are other curves and it changes curvature. So in order to account for all possible shapes of the pectoral muscle edge, we said let's use Gabor filters, but we know the angle range. So the Gabor filters don't have to go again 0 to 180 degrees. So we said we'll just cut the mammogram in this manner by finding the farthest point from this. The mammograms are always arranged so that the pectoral muscle edge is on the left hand side, and find the edge of the breast boundary there and draw a straight line and remove everything else. So now the pectoral muscle, which is on the left hand side, will be there. Sometimes it can come up to here. It is supposed to go at least more than half the size, perhaps up to 3/4 of the height of the image. That's a requirement. So this doesn't meet that requirement. That's what Dr. Desetel told us. So this is defined automatically as a rectangle formed by the chest wall as a left-hand edge and a vertical line through the uppermost point on the skin air boundary. And then we apply image decomposition using Gabor wavelets. I described the wavelets now. Then computation of the magnitude and phase images by vector summation, phase propagation, detection of boundaries by searching for pixels with opposite phase orientation, correction of disjoint boundary segments, and removal of unlikely pectoral muscle boundary candidates. Those are the steps. So this is the first step of delimiting the processing portion. Now let's look at Gabor wavelets, but we will see this at least 2 more times in chapter 8. Gabor wavelets are Gaussian functions. This part is a Gaussian, modulated by a complex sinusoid. But this could be changed to just a cosine function or a sine function as you wish. This includes both sine and cosine. So it's an exponential. If you just take this part, it is a Gaussian. There is some normalization factor. This is not important in image processing because you will be transforming and thresholding. But this part gives you the modulation. So it is a Gaussian function which is multiplied with the sinusoid. So you get a positive main lobe and negative and positive side lobes going to infinity. Then you can dilate, you can treat these as wavelets. You can also treat it as just a function. Take the Fourier transform, you get a band pass filter. There are the scale factors, you adjust them, and you will see the band pass nature of the filters in a moment. And you can use whichever filters that suit your application. You can have as many as you want and make a bank of multi-scale, multi-orientation filters. But in this case, for his own interest, Ricardo, he said we will use the wavelet formulation. Doesn't have to be so, but that's what he did. And in the case of wavelets, you need a scale factor and you need rotation, in this case for directional analysis. So psi mn xy is a to the minus m psi x prime y prime, where x prime y prime are the rotated coordinates. Some origin x naught y naught. This is simply the rotation transform by angle theta n. And do it for all angles of interest. Okay? Scaling, rotation. So theta n is some n pi over k, as many steps as you want. In the frequency domain, you get bandpass filters. The Fourier transform for Gaussian is a Gaussian. You are modulating it and rotating it. Rotation in the space domain is rotation in the frequency domain by a corresponding angle. And scale factor will shrink or expand that Gaussian. And the modulation will place it at a certain position depending upon the modulating function frequency. So it turns out to be, this is a Gaussian, but U is shifted by this W, that frequency, the modulating frequency, capital W. This is just a Gaussian. That is multiplication by another exponential j2 pi wx, which is cosine and sine. So in the frequency domain, UV is a frequency domain, you have another Gaussian shifted in one frequency. And these are the scale factors. These scale factors are inversely related to the scale factors of sigma in the space domain. The design strategy is to project the filters so as to ensure that the half-peak magnitude supports of the filter touch one another. So these are Gaussians. Each one is a Gaussian in the frequency domain. But it goes on forever or to the end of that, whatever the array is. But at half of the power point, you say, okay, that's enough. And you want the next Gaussian to sit at that point so that you don't get gain less than half when you use multiple filters. So this is how it looks. There are 4 scales. As you scale the function, the Gaussian function, each one of these ellipses is a bandpass filter. The position of that bandpass filter is determined by the scale factor, low frequency, medium frequency, and high frequency. And the angle is given by the rotation. And W determines these placements. So we have these multiple parameters, A, sigma, X, sigma, Y, and W, and the theta. So if you want to have the full range, then you would use all of these filters. We are showing here S equal to 4 scale factors, K equal to 12 angles. And these are the UL and UH are the frequency cutoff parameters. If you want to get output in all angle bands, then you would use all of these filters, which are, there are 48 of them, bandpass filters. But we know that the pectoral muscle is only in that range, some range position in that angle. So we only use these perpendicular to that angle in the image domain. So these 3 angles and 4 scales, we use only those filters, or the output of those filters. And the DC gain is set to 0, so that intensity information is removed and you meet the conditions required for the wavelets. So this is 0 here. Depending on the scale factors you use, you will get different shapes of those Gaussians in the frequency domain. So you have this parameter A, UH over UL to the power of 1 over S minus 1 scale factor and the cutoff frequencies. In the frequency domain, sigma U, sigma V are related to those other parameters. You don't have to read all of that. But they are related to the parameters you specify in the space domain and the other design parameters I mentioned. So UL, UH are the lower and upper center frequencies of interest, K and S are the number of orientations, number of scales, and sinusoid W is set equal to UH. Now, we are dealing with real images with positive contrast. The objects of interest are denser than the background. So you don't need sine waves in the complex exponential. You only need cosine functions, so you only take the even part of these functions. You don't need the complex wavelet. So there are some design parameter choice made here. I'll skip all of those and go to the detection part. After computing the phase and magnitude images by vector summation, there is vector summation of those 12 outputs. Now you have different scales and different angles, and how do you combine them? You use angle as the phase and the magnitude of the Gabor output at that location as the magnitude in composed vectors, because you only had 3 filter angles. The edges could be at any angle in between them. So you use vector addition. The magnitude AXY and phi XY phase at each location are used to represent edge flow or some kind of an oriented pattern. So there is a phase propagation algorithm. I won't go through this. You can read this later on. But instead, let me show here. This is the pectoral muscle edge, and you have these vectors indicating the direction of what he called phase propagation, the phase of these outputs of the Gabor filters combined as vectors. So when you have opposite phase, then that is where you have the edge, because you have the gradient this way and gradient that way, and that's where the edge lies. So by finding these pixels, and there is one more set here, we get the edge, or edges, as many edges as are present in the image. So here we have the result. Again, I'm skipping some parts. You may read them, or I think the pictures will tell the story. Minor details need not be of concern at this time. So here we have the pectoral muscle. This is the part of the image chosen for processing. There is a little bit more of the breast image there that was removed initially. And this is the Gabor magnitude output, the edges, and this is after some processing to remove other parts that are too far from this boundary and they don't touch the upper boundary. The pectoral muscle edge has to touch the upper boundary. So these other pieces can be easily rejected. So you do get multiple lines from the Huff transform because there are multiple peaks that pass all the criteria. So out of all of these lines, which one do you want? You take the longest one, and it has to cross there, it has to cross here. So that is the pectoral muscle edge. There is something here which most likely is a lymph node, but the edge goes through that. I'll skip some of these parts. We don't need these. Let's go to look at some results. The false positive and false negative pixel counts were computed for all of the images in the test data set in relation to the pectoral muscle boundary drawn by a radiologist. And the results were evaluated visually by the radiologist and also in terms of these. And the images were ranked in terms of false positive and false negative both being less than 5% or 5 to 10% or more. And the results with the Huff transform, there were 66 images having false positive, false negative greater than 10%. With the Gabor, that reduced to 17. So the output of the Gabor filter is a better approximation of the pectoral muscle. So some more examples. That's using the Gabor filter. That's using the straight line. So the pectoral muscle edge comes here. The straight line doesn't catch it, but this one does. This is a good straight line. Gabor filter works. Not a perfect straight line. The straight line is giving a little extra breast tissue there and missing some pectoral muscle edge there. In some cases, there could be two edges to the pectoral muscle. There could be a major muscle and a minor muscle. And then there could be confusion. But the method worked well. We got this edge here by choosing the longest line. Both of these lines meet the conditions. Well, here it doesn't. It doesn't meet here. It meets the top. So if you were to put the extra condition, it has to cross here too, then that goes. And all of these lines fail. Okay? Any questions or comments about this? Riccardo Ferrari, he did a lot of work on detection of the breast boundary, pectoral muscle, the fibroglandular disc, Gaussian mixture modeling, and bilateral asymmetry for his PhD. That's a lot of work. We wrote many journal papers based on his work. So all of this is based on his PhD work. The next one is fuzzy set based fusion of contours and regions.
When uploading this Gabor filter on entire image, there could be something inside the breast, some calcification or something get detected.
Not calcification, but the fibroglandular tissue. Fibroglandular tissues, they will come up later on in chapter 8 in the detection of tumors. Fibroglandular tissues will have sort of curvilinear structure patterns. So if you use Gabor filters for the entire image, you will detect the fibroglandular tissue patterns. And we have used them in the analysis in the detection of architectural distortion. I'll go into that at the end of chapter 8. So yes, Gabor filters can detect many other things. Here, it is an overkill to use Gabor filters.
White patches were there in the bottom side of the image.
Yeah. No, but we were looking for straight lines only in the half transform case. In this case, we put other conditions that these lines must cross the upper boundary and the lower boundary. And the lines that you get within the breast will be short lines. So they will all be rejected. I showed some of them passed the test. But they will not be as strong as the pectoral muscle edge. But if you apply the Gabor filter, and we have done that, the full range of Gabor filters to the full mammogram, then we can detect all fibroglandular tissue. And we can use that for the detection of asymmetry and architectural distortion. So that comes up again later in chapter 8.
Is there any use of using multiple filters on the same image?
Multiple?
Multiple filters, like different filters on the same image. Can we use it?
We have used multiple Gabor filters, different orientation and scale here. But
on the same parameters, you are just changing the parameters of the Gabor filter. I'm asking like Gabor filter or half transform Gabor filter or problem. Is there any problem in that or advantage in that using it?
other filters were used for example, low pass filtering to remove noise and so on. But it depends on what you want to detect. Certainly, there is nothing preventing one from applying multiple different types of filters and getting their outputs and combining them. But it depends on what you want to detect and what you want to do. So in this case, we want to only detect edges. And Gabor filters, being bandpass filters, will detect edges. As I said, you don't need Gabor filters in this case. But then we limited the range, angle range, so we didn't use the entire angle range. And we used vector summation using only 3 angles. So computation was not that high. We wanted multi-scale. Even that perhaps is not required here. Multi-scale just for the edge is not necessary. Whereas if you want to detect all of the fibroglandular tissue within the breast, then you need multi-scale and full orientation, 0 to 180. And if you want to apply other filters before, you could do for pre-processing. Along with Gabor filters, I can't think of which other filter you would put, but it depends on what you want to detect.
So there's no edge format, right? It's no edge format.
Yeah.
Is it a vital code to get edge format?
Oh, this work was done long ago, and if you want, I can give you the email contact for Riccardo Ferrari. He has the code. I don't keep the code. But this was done more than 25 years ago. I don't think it was Python. It would have been C++ or something. I don't look into the code of my students, but I do check the results. I sit with them and look at the results. And the code is theirs. And in most cases, the next student who comes will say, oh, that code is bad, and write a new code. And the next student comes and says, oh, that code is bad. I have seen that repeatedly.
I've seen the people's edges were there, but along with that there was an edge format. I just want to know how that, the code or something like that.
If you want, please send me an email, and I'll connect you with Ricardo. He's in Brazil.
The advantage with the Gabor might be like multi-scale and multi-orientation.
Correct. But scale is not important here. It's only the edge you want. So there is no scale in the edge. But wavelets were topic of interest at that time. Gabor filters in multi-scale formulation was a topic of interest, so it was used. But perhaps it could be simplified further. You don't need all of that information. But it worked, so it's there. So this is going back to the work of Denise Gugliato. She's also in Brazil. And we did some collaborative work on fuzzy set image processing or fuzzy set based image processing. I showed you fuzzy region growing and then getting the contour, and then a fuzzy region growing method that gave a region, a fuzzy membership region for the tumor. So one method gave a contour, another method gave a fuzzy region with fuzzy membership with no contour. And later on you will see another method another student of mine developed to detect tumors that gives another boundary. So in your bank of programs, you may have multiple programs to detect something. And one gives a contour, one gives a region, another gives a fuzzy membership region. So which one do you take? Or could you possibly combine them all and get one result that is better than any one of them? So for that, Denise said we will develop a fusion method where we can take all of these and fuse them by using some operators for fusion. Now some of the terminology here is computer science based, so I had a bit of difficulty with that, but let's see how it goes. So can the problem benefit from the use of multiple approaches to detect something? And when you get multiple results, instead of looking at all of them, can you put them all together and get possibly a better result? So we already saw one to get a contour, another to get a fuzzy region. So what is a fusion operator? It says you have fuzzy sets defined in this manner, and you map to 0 to 1, and n greater than 2 or equal to 2 will represent the number of sources of information. So there are conjunctive, disjunctive, and compromise operators in fusion. An operator is conjunctive if when you combine a number of these inputs, the result is less than equal to the min of all of these put together. That's a consensus. It is developing a consensus between these. It is a generalization of intersection, and it is severe behavior because the result is lower. Disjunctive takes greater than equal to max of all of these. And it is permissive, it allows all of these opinions. And it agrees with the source that offers the greatest measure and redundancy between criteria. And a compromise operator is something in between. And it is cautious behavior. So you have these sources coming from multiple methods, contour, region, and so on. But how do you include or combine a contour with a region? So these are context-independent, constant behavior operators. They maintain the same behavior independent of the input variables. So let's look at this picture and then we will see. So there is a contour. SC is a contour. SR is a region obtained by region growing. And there could be some artifact there. The region may include parts that are not included or members of the region. So a fusion operator designed to aggregate such entities should produce a third entity that takes into consideration the inputs and is better than either input. So the fusion operator must be able to identify regions of certainty and uncertainty. Where do you have high certainty and where do you have uncertainty? You have high certainty here and along the boundary. But you need to include the others too with a fuzzy membership. So there are 4 situations here. The points on the contour, points inside the contour, points inside the region, and points of the region inside the contour. That is obtained by contour detection, and this is by region growing. So all pixels in this region are members, and only pixels on the boundary are members. So you need a mapping. So there is a membership degree P, and there is a mapping that goes from SR to I in the range 0 to 1. This function is 0 when the pixel P is inside or outside the contour. It's equal to 1 only on the contour. Now you may say, well, everything inside the contour belongs to the object. That's possible, but certainty exists only on the contour because that's what is given to you. And it possesses a high value and P is on the contour. Similarly, it belongs to the region and it is low or 0 when it does not belong to the region from the other input. So the fusion operator, 4 situations arise. P belongs to the intersections of the two inputs, SR and SC. In this case, P belongs to the final segmentation with high membership. Both are telling that is inside. So the sources agree with respect to the inclusion of P in the final result. It is certainty. And the second, P does not belong to SR or belongs to SR with a low membership if it is a fuzzy region, and is inside the contour. So this is a case of uncertainty because we don't know if this intersection, let me just see here, it does not belong to SR, okay, it's outside the region. All belongs to SR with a low membership degree. So the region growing method says the membership is low. So there is a case of uncertainty. P belongs to a contour line of SC and does not belong to SR. Then this is also uncertainty. The fourth one, P belongs to the region with high membership but is outside the contour. So this is also uncertainty. So going back to that picture, we have these 4 situations. Certainty here, the others are uncertain. Here we are on the contour, but the region doesn't include that. Let me go to some of these The fusion operator is defined by a finite automaton that aggregates the n sources by having this pair H. H is made up of these points that are fusion operators, and they map the input to the range 0 to 1. I'll skip some of these details. You could read them later on. I don't want to read all of that. There are just the rules there. Let me. Okay. So we had the contour. The contour drawn by the radiologist is shown for reference here. I showed the contour obtained by segmentation earlier and the region. When you combine them, you get this. And if you were to compare with the previous picture, you see that the fuzzy membership computed by fusion, which is shown here in different levels of gray, is having a high value of membership inside the contour given by the radiologist. By the way, that contour by the radiologist was drawn independently. He didn't have this figure or this result. And there are low values here, but there is not much outside. This part was included in one of the methods, but now these pixels have low membership value. So in a way, this result is better than the other two by using these conditions. This is a benign mass case where you don't see many pixels with low membership, and the high membership values are all included within the contour given independently by the radiologist. I showed these results earlier. You could compare them with those figures later on. Here is another case. There is a dense mass here, and let me go and check which is which. Contour extracted by fuzzy set. Black is the radiologist and C is fuzzy region growing. Okay. So the black line is the contour drawn by the radiologist. The white line is obtained by region growing using the fuzzy set pre-processed image. So it includes the mass, but there is some excess material here. This was obtained by the fuzzy region growing method, which is not bad actually, except for a little bit there. Most of it is contained within the reference contour. And when you fuse them, what was outside, the excess region in the contour now has low membership. So some of that was outside the contour, but not in the fuzzy region, is not exactly rejected, but the membership is low. There are many pixels around the boundary that have low membership. So we found that this was a good indication of malignancy of the mass. This is a speculated malignant tumor. And go back, this is benign, and this is also malignant. So in the case of a malignant tumor, you see pixels around the boundary having low membership because the boundary is fuzzy, the tumor is not well defined, and the tumor is spreading. So fuzzy membership in this case does relate to the malignant nature of the tumor, whereas in the case of a benign mass, the membership is sharply defined right up to the boundary and not much beyond. And here, this is also malignant, and you do have a number of pixels around the boundary that have low membership. So this we took to define a measure of fuzziness. If there is fuzziness in the boundary, I'll just skip all of these definitions. We don't need this for now. The result was evaluated by just comparing these images before and after fusion, so I will not go through that. There are some numbers here that are not important. So I'll just skip all of these for now. If you want, you can read those later. So to end this chapter on detection of regions of interest, we have looked at several methods, and we have studied methods to detect objects of known characteristics or geometry, and how to improve initial estimates. After regions of interest have been detected and extracted from a given image, they may be analyzed further to represent features, or in terms of representation, to do feature extraction, get some parameters that represent the distinction between the categories of interest, shape, texture, whatever, and those should help in pattern classification and image understanding, eventually leading to computer-aided diagnosis. Now, how do you characterize regions, which is the topic of the next few chapters? There are external characteristics, boundary or contour morphology or shape, boundary roughness, boundary complexity. And typically we would want the boundary descriptors and any descriptor in general to be independent or invariant to translation, scaling, and rotation. If it is rotated or if it is translated, it should be the same. Scaling, if the object is that big or this big but has the same shape, that is, take a picture from here or from a distance, the characteristics you measure must be the same, must be invariant to those. Internal characteristics of the region, grayscale, gray level, color, texture, statistics of pixel population of what is inside the region. And then after you extract the features, you want to compare the regions in terms of similarity or dissimilarity. Are these regions similar or not? You can do direct pixel by pixel cross correlation, template matching, and so on, but we don't want to work with pixels anymore. We want to extract features that combine all the information present and be independent of individual pixel values, and instead use the features that we have designed based on what we have learned from the domain experts. So for that you could use distance measures and correlation coefficients between the feature vectors, not the pixel values. But that is pattern classification, which I have in the last chapter in the book, but my book is not on pattern classification, so there is just a quick review of basics of pattern classification. But the best book available is Duda and Hart. A relational description. You have multiple regions that you have detected. What are the placement rules? How are they placed? Some kind of a grammar to connect them. Structural description and syntactic analysis. Describe each one and then describe somehow how they are placed, how they interact, how they are, what is the interplay between them, such as a cluster of calcifications. You detect each calcification, but then you have to put all of the information together. How many calcifications did you detect in the image? Are they placed in a small area in a cluster, or are they distributed at random? And if they are placed along a straight line, like a duct. So these are important, and that would be the relational description between multiple regions that you have detected. Not much in the case of tumors, but tumors could contain calcifications. So you want to know if a tumor you have detected contains calcifications. So that would fall under relational description. That finishes the chapter on detection of regions of interest. I skipped a lot of details. Reading them or going through them doesn't fit in a course like this. You may read them if you are interested in those. What else did I want to say? That's about it. I have skipped a lot of details here. I want to keep some time, if possible, to include another research seminar later. And I want to go through texture and oriented pattern analysis in detail. In the files I have sent for you, you have chapter 7 and 8, and there is a file called texture analysis, which is just a few parts extracted from 7 and 8 that I give as a seminar on texture analysis if I don't have the time to go through the material in detail like this. But I think we will have enough time to go through 7 and 8 in detail as much as possible. I'll skip some parts again to keeping the time in mind. But next we have analysis of shape, which will take up